Now we're going to discuss method of corners. So here's an example. Solve the linear programming problem using method of corners. We are going to maximize p equals x plus 2y subject to negative 2x plus y less than or equal to 4, x minus 3y less than or equal to 3, x is greater than or equal to 0, and y is greater than or equal to 0. So let's label a few things. Remember, this is your objective function, and these are constraints. So let's talk about two of these constraints in particular. These two right here mean that x and y are both non-negative. We classify numbers three ways according to sign: positive, 0, and negative. So we're saying x can be 0 or it can be positive, y can be 0 or it can be positive. What this really matters, though, the reason we care, is that we are now looking at quadrant 1. Whatever region we end up graphing, our answer will only be in quadrant 1. Okay, so we're going to start this by graphing this system of inequalities. We're going to ignore the objective function. That is not going to be part of our graph. Okay, so let's graph our constraints. There's a whole video I've made showing step by step how to graph this, so I'm going to go through this a little more quickly. You're going to think about this as negative 2x plus y equals 4. The fastest way to do this is to let x be 0, cover it up with your finger, it's gone. If x is 0, then y is 4. And we do the same thing with y. We're going to let y be equal to 0, so cover it up with your finger, pretend it's not there, and you have negative 2x equal 4. Solve that equation. You divide both sides by negative 2, so you end up with y is 0 and x is negative 2, because you're doing this in your head. Okay? So we're going to have those points as our intercepts. And as we've mentioned before, it's convenient to graph these systems with intercepts because often the intercepts are going to be corner points, which are going to be relevant to method of corners. You could solve and get y equal mx plus b form and find the y-intercept and then use the slope. That is appropriate, but it takes too long. So we're going to go the fast way. We look at the second equation, write it as an equation instead of an inequality, and we let x be 0, which means cover it up with your finger, it's gone. Now you're going to solve negative 3y equals 3. So when x is 0, y is a negative 1, because you're doing this in your head. Okay, remember when x is 0, we get the y-intercept, and that is what the point 0, negative 1 is. Now we're going to do the same thing. We're going to let y be 0 this time. So if y is 0, cover it up with your finger, pretend it's not even there. Then you can read off that x would be 3. So if y is 0, your x value is 3. Okay, so now we're going to make our graph as big as we possibly can because we want to be able to see all of the nuances. And we notice that our biggest number for the x and the y is 4, and our smallest is negative 2. So we're going to use our scale based on that. Okay, so I've drawn the x and y axes, and I have labeled the tick marks. I'm going to use 5 as my max because the x and y coordinate that I see the biggest is 4. I want to make sure I have a little more room. And you notice my graph focuses mainly on quadrant 1. There are 2 points that are not in quadrant 1. We're going to use them to draw the lines, but our shading will be in quadrant 1, so I want that to be the focus of my graph. Okay, so now we're going to plot these points. For the first equation, negative 2x plus y equals 4, we're going to graph the line, so we're going to plot that first. We're going to plot 0, 4. It's a y-intercept, and the x-intercept is negative 2, 0. So we plot that. We connect them in a straight line. Notice the line is solid because we have this inequality less than or equal to. There's an equal part, so we use a solid line. We label the line. Remember that you're labeling the line, so you use an equal sign. Let's graph the second line. X minus 3y equals 3. So we're going to plot the points 0, negative 1, this is the y-intercept, and 3, 0. Again, we're going to connect these. We label this line, x minus 3y equals 3. We're labeling the line, so we use an equal sign. Now we're going to shade our region. We're going to pick a test point. It is convenient. Looking at the first line, negative 2x plus y equals 4. A convenient test point would be the point 0, 0. I want to pick something easy that's easy to manipulate. 0, 0 is not on my line, so I'm allowed to use it. So I'm going to use a test point 0, 0, and I'm plugging into negative 2x plus y less than or equal to 4. When you do that, x is 0 and y is 0, so you get 0 plus 0, left-hand side is 0, 0 less than or equal to 4. That is a true statement. So we're going to shade the side of that line that contains the point 0, 0. So here's 0, 0. I want to shade this part of the line. I'm going to do it a little more carefully though, so that I can see what's shaded for both pictures. So I'm just going to do maybe some arrows so I can sort of see the direction. Then we do the same thing with the other line, other inequality. We're going to pick a test point that's not on the line. 0, 0 is again appropriate because here is the line. 0, 0 is not on that line. So I look at x minus 3y less than or equal to 3. Test point says x is 0, so is y. So if I plug in x and y both equal to 0, the left-hand side becomes 0. 0 less than or equal to 3. This is a true statement. So we're going to shade the side that contains the point 0, 0. So here's 0, 0. I'm shading this way. Okay. But again, I want to make sure I do it in a kind of a simpler way so I can actually see what's going on from both lines. So I'm going to put little arrows like this. And then we see we have the inequalities where x and y are both non-negative. So that means we are looking only at quadrant 1. So we're going to look at what these have in common. And I'm going to shade it in yellow. So we're going to use this boundary and we're shading everything down from this line. Keeping in mind, I'm not going anywhere to the left of that y-axis. I'm only in quadrant 1. And then I'm above this x-axis because I'm in quadrant 1. Like this. Then I get to this line right here, x minus 3y equals 3. And I'm shading above that. So my feasible region S looks like this. And you can extend this on and see that this goes on forever. S is what we call unbounded. Okay, now we're going to do the method of corners. So we have to figure out what our corner points are. Well, how many corner points do we have? Remember, a corner point is found by looking at an intersection of some of the constraints. So we see that this is a corner point. It's the intersection of x equals 0 and negative 2x plus y equals 4. We see that this is a corner point. It's the intersection of x equals 0 and y equals 0. And this is also a corner point. It is the intersection of y equals 0 and x minus 3y equals 3. So we need to figure out what those points are, what are their coordinates. So I'm going to label them A, B, and C. And if you look, as I told you earlier, often our corner points are going to be intercepts. So if you found intercepts, then you're pretty good. So A is the point 0, 4. C is the point 3, 0. And what's B? Well, B is the origin, so B is 0, 0. Now we're going to do method of corners. So what we're going to do is we're going to put our corner point in this column of our chart, and we're going to put the objective function over here. We are going to maximize P equals x plus 2y. Our corner points were A, which was 0, 4, B was 0, 0, and C is 3, 0. So remember, this is x, y, x, y, x, y. So that means we're going to let x be 0 here and y be 4. So we end up with P equals 0 plus 2 times 4, which is 8. And you can do that in your head if you want to. I'm just showing you where the pieces come from. And then we see P is again x plus 2y, but my values for x and y are different. Now P is x is 0 and y is also 0. So you get 0 there. A lot of students will just say, well, they can do that part in their head. But if you need to write it down, write it down. Then in the last case, x is 3 and y is 0. So P is 3 plus 2 times 0. P is 3. So we do method of corners, and we see that we get 8, 0, and 3. And you say, well, which one's the max, right? Well, the max is 8. You may be tempted to say the answer is 8, but it's not. This actually has no solution. No solution, because if our feasible set S is unbounded, we can't find the maximum. So you really didn't even have to do this work right here.